Good morning and welcome to today's webinar. My name is Beth Capellis and I'm the Sales and Support Manager here at Triangle Microworks. Thanks for taking the time out and joining us today. Triangle is hosting a free multi-part training series called IEC 62050 Hands-on Training. Today we are presenting Part 1, Foundations of IEC 62050 from Legacy System to Digital Substations. We will have future training modules that will cover such topics like data modeling and SEL introduction, bottom-up versus top-down IEC 62050 engineering process, testing, commissioning, and virtual isolation, as well as many other topics. If you're interested in receiving updates on when these other training modules will be held, please answer the survey at the end of the webinar and you can sign up to receive those notifications. So before we get started, I'd like to go over some housekeeping items while everyone is still joining. The training is scheduled to be 2 hours long. The audience is on mute, so please submit your questions online using the webinar toolbar under the section titled Questions. You can submit questions as soon as you have them. Please don't wait until the end. We will begin answering questions online as we have several engineers monitoring those questions and responding to them directly. We do have a lot of material to cover today, so we'll most likely save questions for the end. Your best option is to submit them online, where you should just receive a direct response. I'd also like to call your attention to a handout that is available from the webinar menu. If you look over to the webinar panel, you'll see a section titled Handouts. If you click on Handouts, you'll find an IEC 62050 Training Series Quick Reference Guide. You can download it directly from there. Now, with that, I'd like to introduce the folks that are behind the scenes answering the questions. Today, we have with us Jim Coates, President of Triangle Microworks, and Christoph Brunner, President of IT for Power. Next, I'd like to introduce our speakers. First, we have with us Jackson Moore, Application Engineer here at Triangle Microworks. Jackson received Bachelor's of Science degrees in both Electrical Engineering and Computer Engineering from North Carolina State University and has a background in Power System Engineering. Prior to joining Triangle, Jackson spent 5 years as a microgrid system engineer, where he designed and developed load management control systems for multi-source microgrids. Currently, Jackson works with our customers and development team to understand and solve the challenges our clients face. Next, we also have with us Matt Green. Matt is a senior application engineer here at Triangle Microworks, bringing a decade of experience to the role. Matt serves as a technical trainer, providing direct customer support, conducting product demonstrations, providing one-on-one or group trainings, as well as hosting webinars. Additionally, Matt works as a quality assurance tester, specializing in the company's simulation tools and gateway. So now that you know everyone, I'd like to give you a little background on Triangle Microworks. We were established in 1994 and have over 30 years of communication protocol experience. We're headquartered in Raleigh, North Carolina, and have customers in over 70 countries. We work mostly with equipment manufacturers, electric utilities, and system integrators. The products we offer all support the standard SCADA protocols and fall into 3 categories. First category is source code libraries. We license source code directly to manufacturers for use in their devices and systems. This allows a much faster time to market and greatly reduces their cost and development time. Licensing a source code library also includes support for your implementation and any issues that may arise in the field. We also provide testing tools supporting these libraries and protocols. These tools are used for communication testing in the lab or the field. They're designed to troubleshoot, simulate, and automate testing for both a single device or complete substation. Lastly, we also provide a SCADA data gateway supported on both Linux and Windows for protocol translation and data concentration, with standard SCADA protocols as well as OPC. It is available as software only or pre-installed on hardware. We are heavily involved in the standard committees that support SCADA protocols, like UCA Group for 62050 and DMP user and technical committees. Through our participation, we help define the protocols, stay up to date on the changes taking place, and ultimately provide feedback based on our customers' needs as the protocols continue to evolve. So now that you know a little bit more about Triangle, I'd like to go ahead and hand it over to Jackson, who's going to kick off the training. With that, Jackson, I'll go ahead and make you presenter.
All right, thank you, Beth. All right, can you see my screen?
Yes.
All right, thank you. So, as Beth said, today we're going to be doing a presentation on IEC 61850. This is a little bit different from webinars that we've done in the past. Here, we're really looking to do, really lay a framework that we'll be building on through this multi-part series. So today we'll be looking at kind of the 10,000-foot view, highlighting a lot of the concepts that we're going to be diving into deeper on in future webinars, but hopefully exposing you to all of those different parts. So we'll be taking a look at how we got here, a brief history of substations in general, and specifically looking at the protection, automation, and control mechanisms that have evolved throughout the ages. We'll be taking a look at some of the legacy systems, so point-based communication protocols. So that'll include Modbus, DNP3, 6870, that'll include 101 and 104, and we'll introduce each protocol and highlight some of the changes that were made along the way, ultimately in the context of bringing us to IEC 61850. We'll take a look at the semantic data model, the different communication protocols, as well as the engineering process that makes this all possible. We'll have several live demos interspersed throughout, so you have an opportunity to see some of what we're looking at or on the slides actually happen in action, and that'll be using some of our software test and simulation tools. So before we get too far in, I want to go ahead and lay the groundwork with a little bit of terminology. I'll be using the words primary equipment and secondary equipment a lot. And I just want to quickly define what I mean when I say that. In the context here, when I say primary equipment, I'm referring to the conducting equipment, so bus bars, switch gears, CTs and PTs responsible for measuring currents and voltages or lowering them down to a level where a IED can measure them. Also, power transformers would fall into this category. All of these devices don't really have much smarts to them, and for the most part, they haven't changed a lot throughout the years. Secondary equipment is going to interface with that primary equipment, and that's what's responsible for actually doing the protection, automation, and control, and that's where a lot of the changes that we'll be focusing on today have actually occurred. So, a little bit of a history lesson here. So, prior to about 1980, all the way back to the days of Tesla, this might be what we would have seen as a typical layout or design for a substation. Down at the bottom, we have our primary equipment, our conventional switch gear. Think breakers, switches, maybe even transformers, things like that would also be attached down here. Our conventional CTs and PTs, these are gonna step down our currents and voltages to a level that our secondary equipment, displayed here in the middle, can measure. Now, at this time, these would have been electromechanical, much like a circuit breaker that you might have in your house. No real intelligence inside of them, no microprocessors or chips. It's just basically using physics. When current exceeds a certain threshold, a little click happens inside and we're able to trip a breaker, for example. Now, above this, we have our interlocking logic. This might be relay logic to prevent two breakers from being closed at the same time, for example, or even an HMI. At this time, our HMI is just going to be little light bulbs that light up to indicate certain breaker statuses or if certain faults have happened. The key here is that all of this information is transferred via hardwired copper. So an individual wire is running from each piece of switchgear up to each relay, potentially up to the HMI if we need to indicate that status. There's no communications going on here. There's just a large network of dedicated copper wires, one for each signal. So beginning in about 1980 is when we switched over to a design that has a couple big changes. So the first is that we're now using microprocessor-based relays. So that'll be these devices here in the middle, again, the secondary equipment. Now the fact that they're microprocessor-based means that we're no longer relying on electromechanical functionality. We're now able to have a digital to analog converter, or I should say an analog to digital, inside of these pieces of secondary equipment. So we're taking those currents and voltages that are flowing up from our CTs and PTs, converting them to a method or a way for these microprocessors to analyze those signals with an algorithm that can then issue a trip signal back down. Again, this is still going to be copper going back and forth from our conventional CTs and PTs in our switchgear, but because we have microprocessor-based relays, we now have the opportunity to communicate this information up to our HMIs, maybe via gateway to a control center or a historian via a communication protocol. So around this time in the early 1980s, there started to pop up a large number of these communication protocols. Some of them were vendor specific, while other ones were industry groups or standards bodies beginning to put together these first initial communication protocols, but it was still a pretty fragmented ecosystem. There wasn't a lot of standardization across different vendors. You couldn't always rely on the fact that two different IEDs or relays from different vendors would be able to communicate with each other. So before we go further, I do want to just mention, what does it mean when I say communication protocol? That's all these numbers and letters that we see up here. So I have a quick example. Some of you might be very familiar with what a communication protocol is, but if not, here's your opportunity to kind of define it in very basic terms. So let's say that I live on this mountain over here on the right side, or I'm sorry, the left side of the valley, and Matt, our fellow application engineer, who will be doing some demos in a little bit, lives on this mountain on the right side. Well, initially, if we want to communicate with each other, we might come up with a system of, let's say, fires and telescopes. You could think of this fire, if I light this fire in this designated place, almost like an output, and Matt with this dedicated telescope looking through and seeing that I've lit this signal fire as a sort of input. You could think of this as sort of like a copper wire that you would have in a traditional substation. Now, each time I want to convey some new piece of information, I need to add a second fire to my mountain, and Matt needs to add a second telescope. If we want to have a richer conversation, convey more and more information, we need to add more and more fire pits and more telescopes. You can see the problem. It certainly works and it's certainly very reliable, but as we want to convey more information, we just need more and more. In this case, fires and telescopes, more and more inputs and outputs, more and more copper wires if this was in a traditional substation. So maybe Matt has the idea, hey, what if we came up with something better? What if we just had one fire on each side of the mountain and one telescope? In a communication protocol, you could think of this fire as our transmit and this telescope as our receive, and each side of a mountain is going to have one. And then we might come up with a system, for example, with short puffs and long puffs of smoke to indicate certain letters. So down here I have a Morse code table, and we could see one short puff followed by two long. Well, this is going to correspond to the letter D, whereas Matt is responding over here with one long, two short, and another long. And if we look down at our decoder table here, this is X. So now we're able to transmit a lot more information because we've come up with a framework in order to transmit it. So that is the beginnings of a communication protocol. It just builds on from there. So to recap, what is a communication protocol? Well, fundamentally, it's just a set of rules for sharing information. It defines how and when we share that information, and it includes a lot of other stuff besides just how to decode letters from smoke signals. It might have message format, syntax, synchronization, so that I know, hey, don't send messages while I'm sending, for example, if I'm not able to have a full duplex system. Error recovery and even security might all be rolled up and wrapped into a communication protocol. And fundamentally, we're doing all of this to ensure that both sides can understand what the other one is saying. So picking back up on our timeline here, now that we've sort of defined a little bit of what I mean when I say communication protocols, let's take a look at what was happening in around the year 1990. This is when standardization efforts really came into their own, and we ended up with several different communication protocols. Modbus, you might remember, was on the slide before. That did start out as a vendor specific, but by this time it's become an open standard and has been adopted widely by not just the power industry, but the industrial automation sector as a whole. DNP3 and IEC 6870-5-101 are also developed around this time, and not long after its successor 104. Other than that, though, and the interoperability that we gain from that, by that I mean these different devices are all able to communicate up to a gateway, and this gateway, as long as it speaks these standard protocols, will be able to receive that information. Other than that, the changes are not drastic, and we'll dive into what they are here in a moment. We still have a lot of copper down here at the bottom, and we are able to use Ethernet instead of just a serial connection. But the big change here is interoperability. So now we'll dive in a little bit deeper on those three different protocols, beginning with Modbus. So the key takeaway here is that Modbus is going to be polling driven and that its data model uses a register or point-based system. So let's dive into what those two terms mean, beginning with data model. So data model means that I describe the data that is on my device in basically a list. So you can look at this list over here. On the left-hand column, I have my data type. So for example, a binary input, and then I have an address and a label. Sometimes I might even include a more detailed description. So if I want to be able to read data from this device, I'm going to need this all-important data map. I need to know what data type is at what address and what that data actually is. Without this data map, I might still be able to read data, but I won't be able to decipher it. I won't know, for example, that binary input 1 means that the relay is, or that the trip LED is ignited and that a trip has actually occurred. Now, the other term that I want to focus on here is polling. So polling just means that I ask for data and I get a response. I, as a client, at some periodic interval, am asking my outstation to report back, hey, what's your information right now? And this is the way that Modbus works. I can request data very quickly, but I only get the data back that the value of the data at the specific point that I ask for it. This is in contrast to some of the changes that occurred once we moved over to DNP3, introduced in about the year 1993. So the key differences here are that the introduction of event-driven reporting. So no longer am I just getting data when I ask for it. I can actually enable unsolicited messages and have changes sent to me as they occur, or maybe after some short buffer period to package multiple events together. Or I can still use a polling paradigm, but just ask what changes occurred since the last time I asked. This means that I don't miss data. The other big change will be the inclusion of metadata. With Modbus, if I wanted to have data quality or timestamp, I really don't have many options. I could make a separate register that it contains that information, but I would really be reliant on that data map that I spoke about before in order to know which metadata is associated with each point. So data quality just tells me if there's any sort of problem with that data, and then timestamp tells me the exact moment that the change occurred. So let's say a breaker closed, but I don't get that event until some time later. I can actually see with the timestamp when the breaker closed, even if I don't get that information a couple seconds later. Moving forward, we have IEC 6870-5. So that includes 101 and 104, at least today, that we'll be talking about. 101 was initially released in 2005 and was purely serial based. And then in 2000, we had 104 with the addition of TCP/IP. From a high level though, it's very similar to DNP3. It includes support for event-driven messaging and also includes metadata such as quality and timestamp. But what all three of these have in common is that they're all going to be a point-based protocol, right? So we still need that data map for all three of these protocols, pictured over here on the right, or we won't be able to get information, or at least we won't be able to decode the information that we actually have. So diving a little bit deeper on just highlighting the differences between polling-driven, event-driven, and event-driven polled, and event-driven unsolicited. So over here on the left-hand side, we have just a pure polling-based system, and this is supported by all three, Modbus, DNP, and the 6870-5 family. So we'll see up here at the top, our SCADA system. The terminology that we used here, it might be a client or a master or a controlling station, depending on the protocol. But a polling period will exceed, and I'll request the data. The field device down here, outstation, control device, will send back that data when I ask for it. Now, in an event-driven style, the key change here is that as the data is actually updating, it'll be stored in an event buffer. I still have a polling period up at the top, and when that polling period expires, I request data. Any events that have been stored in that event buffer will then be packaged and sent up to me. So again, I'm no longer missing data, but I'm not getting it right as the changes occurred. In contrast, event-driven unsolicited, I no longer have a polling period. I might send an enable from my client or SCADA master up at the top to enable this functionality, but after that, my SCADA system just sits here, and as data changes, it's packaged into an event buffer. Sometimes we might wait a fraction of a second in case multiple events come in, or we might not. That's up to you as a configuration. But that data is sent up to me without me needing to ask for it as the SCADA system. So what are the ramifications? Why do we care? Well, basically, in a polling-based system, we have the opportunity to miss data. So if you could imagine this blue line here is a signal changing, maybe a breaker opening and closing, for example. And each one of these vertical black lines indicates a time which I asked for the data. Now, I'm going to get the data at these points in yellow. So you'll notice in these first two polls, the breaker's closed, it opens, it closes again by the time I've asked for the data again, and I miss this data altogether. This rising edge indicated here on the left is never captured by the SCADA system. Now I can increase my polling system, but my polling rate, but there's always an opportunity to miss data if it's changing fast enough. In an event-driven style system, I'm still, or at least an event-driven polled, I'm still asking for data at periodic intervals, but both of these changes are going to be packaged together and sent to me when I'm asked for them, and I'm no longer missing that data. And because I have metadata, I can know when that change occurred by the timestamp. Finally, in event-driven unsolicited, you'll notice there's no longer these vertical black lines like we had in the polling-based paradigms. Here, as the changes occurred, they're just sent up to me after, again, some short buffer period, depending on how you have it set. And I capture that system or that data and log it in my SCADA system or historian. So included here is a table. As Beth mentioned at the beginning, everyone will receive a copy of this presentation after it's over. I will reiterate, please go ahead and ask your questions now. Don't feel the need to wait till the end. Just go ahead and use that question button. But I include this table just so that you guys can use in the future it as a reference to see what some of the similarities are and differences between these legacy protocols. And with that, I'll go ahead and kick it over to Matt, my fellow application engineer. He'll be using several different tools available from Triangle Microworks in order to demonstrate some of these concepts that I've just introduced: polling, event-driven, things of that nature. Matt, go ahead.
Thank you, Jackson.
There, you should be presenter now, Matt.
All right, I think everyone should be able to see my screen now.
Yes.
Fantastic. So yeah, I'm going to go over some of the concepts that Jackson just went over and what that looks like inside of the tools. Specifically, the first demo that I'm going to be giving off will be between our DTM tool, which is our distributed test manager, and our test harness tool. Just very briefly, I'm going to be going over our DTM. DTM is our system simulator tool, and it simulates servers, outstations, controlled stations, everything of that manner. It's going to be the environment that I'm going to be interacting with our master and client tool, which would be, in this case, test harness. So you could also just imagine DTM as physical devices, your substation, your system of devices. But since I don't have all those devices on my desk here, we're going to be using a simulator tool. So the first thing that's probably jumping off the page that you're seeing is this single line diagram in here. This single line diagram is a very simple model of electrical equipment that we can interact with in order to change the values inside of our protocol devices. So for instance, you'll see some of these CTs and VTs, so current transformers, voltage transformers, breakers and switches, bus bars. If I go into this QA1, this is our breaker, and just open it, we'll see the current drops to 0, and that can kind of make effects happen on the electrical equipment here. And all of the effects that are changing, the voltage changing, the currents, the breaker positions and stuff, is being reported over to my devices. So let's take a look at some of the devices. Well, that's all held over here on this left-hand pane. This is the Workspace tab. And in here, you'll have things like JavaScript, some behavioral scripts. We even have the single line diagram, which is shown here as a node in this workspace. But most importantly, we have our devices. So obviously, we're going to be talking about 61850 a little bit later, but I have a folder full of my 61850 devices called my IEDs. And I also have a folder called Modbus and DNP. This is going to be the point-based devices that Jackson has been alluding to. So I'm going to go ahead and start changing some values on our DNP and our Modbus devices. And I'll just do that through an auto data change. What an auto data change is in DTM is it just automatically changes your values. And just for the sake of simplicity, I'm just going to be toggling a single binary in our DNP and a single binary coil inside of our Modbus. And the reason I'm going to be doing that is twofold. Number one, if I'm doing polling or reads and stuff and the values are always the same, that can be kind of boring. You're not going to get very much info. But more importantly, once we move on to the event-based polling, we will be needing to generate traffic and events such as the rising and falling edges that Jackson was showing off previously. So I have pulled those 2 points out and put them in a little table down here. So while this auto data change is going, it should be changing data about every 2 seconds or so. We can see those values here. Of course, you could extend this out to anything that you'd like. The full database is displayed within DTM if you wanted to, but since these are the only 2 points I'm changing, this is just what I'm showing off right now. So now that we've got some data changing in our simulated environment, or you can imagine it as our real world environment, we can move over to our test harness tool. So this is our test harness tool. Let me go ahead and make it full screen. And it's laid out in a similar way as DTM. This is a separate application to DTM. And right now it's laid out, you'll see right here in the middle, this is what we call our protocol analyzer. And what this will do is it will go to the bits and bytes on the wire and actually take them all in and convert them into a more human readable way. So we can see at the very beginning, we had our MDNP, so that's our master DNP3, connect up and issue out time synchronization. I can tell that's coming out of the DNP, the master, because the arrow is pointing away. I also can tell that that's at the user layer because you can see in the filter has plus symbols, and that's what the tail of the arrow looks like. So you can say which way the traffic is coming in and out. What we're going to see a little bit more is potentially responses to things. So for instance, when it first connected, the DNP device needed to build up its database, so it sent a read request, and eventually the SDNP responded with that and gave all the binary inputs, the double bits, the binary counters, frozen counters, all that type of stuff. So all that happened automatically when we first connected, but let's go ahead and show that off how you can do it manually. So I'm going to go ahead and clear out the protocol analyzer here, and I'm going to hide away DNP right now and just display the stuff that's going on with Modbus. So to see the database that we have inside of Test Harness, you can go up here to Open and down to the data window. We'll see our 2 devices here. I can open this up, and now we see our coils, our input registers, holding registers, all of those things. Now I can go to each of these folders, and we'll notice there's no points in here. Well, that's because Test Harness hasn't been told to actually go out and pull in that database yet. So we can do that by going back to Open and doing a command window and doing Modbus. Now we have access to the commands that we can issue, such as reads and writes. Those are the primary 2 that you'll be looking at with Modbus. So if I just left click this read coil here, it'll go out and issue the read coils. So we can look in the historical protocol analyzer here. The command window initiated a read coils. The settings for that was start at 1 and read a quantity of 1. That gets all boiled down into the Modbus protocol, which is then sent out the read coils starting at register 1, quantity 1, and sure enough, it gets a response to that, including coil 1 equaling 0. So when I go back down to our data window here and go to coils, we now have access to that. Now, it's a little bit of interesting information to point out here is exactly what Jackson said, which is the metadata surrounding some of the points, such as quality or timestamp, is not necessarily included in Modbus. So we'll see this flags section here. That's where we would normally put quality, online, offline, needs attention, bad, whatever you want to set as your quality. Well, Modbus doesn't support that, so we just put NA. And while the data itself did not come with a time updated, Test Harness does know when it itself received that. So you can go ahead and assume a timestamp for that, but the data could have changed, a week ago or something. And if we pulled it just now, that's the timestamp that we're going to get. That's why it does have assumed next to it. So now that we've done that, I can also show you that if we go back into the commands here, instead of left clicking, you can actually come in and right click and configure the command. And when you do that, you'll have options here. So by default, it was just reading a coil, starting at 1, quantity of 1. If you just hit once, it would repeat the same thing. This is all editable within this testing tool. So I could come in here and say, I want to start at 0. I know that's the point I'm changing within our simulation. And maybe we just want to read 5 different points, right? So now if I click once, it'll go out, it'll send that read coils request, and it will do starting at 0 and reading quantity of 5. And sure enough, we're seeing coil 0, 1, 2, 3, 4 with the 0, luckily being on the on state rather than the off state that everything else is. So that's how you can get additional data. Jackson did mention that you could periodically send requests, and you can do that in Test Harness as well. So if I want to set this down to maybe 4 seconds, and I will set this just back down to 1 value to read, I'll clear that out so we have some more real estate there, and I click start. What we'll see is now every 4 seconds, we're sending out this read command. But what we're also seeing is that the coil's coming in as 1, and then it's coming in as 1 again, and then our third iteration, the coil's coming in at 1. And that makes sense. Even though I know in my simulation the data is changing, the rate at which I'm polling is not enough to actually catch all of the state changes. So if I go back to DTM here, we'll actually see the values are changing, but at a rate that's faster than we're pulling in our Test Harness tool. So as Jackson mentioned, we could increase this interval, or we could move on to more advanced tools and features, such as the ones that DNP support. So let me go ahead and stop this now. I'll close it. And I'm going to swap over to DNP3 here. So now that I'm in DNP, obviously you can do exactly like we did before. So I can bring up the data window. Since it did a integrity data poll, which just grabs all of the data when they first connected, I actually have access to all the binary inputs, the double bits, the output statuses. I already have access to all of that. But you will notice that the value isn't changing, and the reason the value isn't changing is for the exact same reason that the values weren't changing in Modbus, which is we're not sending any consistent commands. We haven't enabled any sort of reporting. So I can go to open, command window here. I'll bring up DNP this time, and you'll see we have a few more options now. We have integrity data poll, report by exception, reading specific types, controls, and then unsolicited messages. Just like Modbus, you can read specific values either once or on a periodic basis, and you can pull that values in, but you still potentially might miss data. And so what we are going to be looking at next is this here. We're going to be moving to the event-driven poll. So this is just the slide that Jackson brought up. The Modbus that we were showing previously with our polling period is over here, and we're going to be moving on to event-driven polling and then eventually unsolicited. So how you can do that in DNP in Test Harness is you just go to RBE, that's report by exception data polling. And if you just click it, it'll send out the report by exception. And then we will see any of the data that has changed in an event coming across. Now, once I clear this, if I come in and have already received those events, if I do it again, now we're only seeing the binaries coming through. So the very first time I sent a message, I said, give me all the event data I've never seen before. And it gave me everything that has happened since I started doing this demonstration. The second time I clicked the button, only the binaries were changing, right? You can actually see that right here. This binary input is going on, off, on, off, on, off. That's reminiscent of this here. So once we start polling at a certain interval, we can start getting the events. And you can even see the same event, that same binary, coming in and showing you the different states it was in. And so if I wanted to match that diagram completely, I could go in here and configure and then do a repeat interval on this report by exception to get the event data. But I can actually take that one step further and go into the unsolicited messages. So this is the master DNP telling the outstation, hey, I'm interested in a certain specific set of points, and I want you to tell me after a certain period of time, package all that information that's changed and send it to me without me asking. So if I go ahead and click this here, and I'll pause, what we'll see is, yes, I initiated that enable unsolicited message, and the master, in fact, at the application layer did send out this enable, and we received a response that it had been enabled. Of course, then it packaged up all the event data and sent it to me. But now, even without me interacting, there's no periodic polling going on. I'm not, interacting with this. I'll be getting messages coming across the line as the outstation continues to push that data to me without me necessarily asking for it. This will help save bandwidth on your network and, constantly repolling the same values that aren't changing. It's just going to give you the important stuff that you need to know since the last time. So with going over some of the point-based stuff and how to do event-based versus regular reads, I'm going to pass it back over to Jackson as he goes more into 61850, and I'll be preparing a demonstration to show off some of the 61850 tools later on today.
Okay, Jackson, I'm going to make you presenter. You should have the screen.
All right, thank you, Matt, and thank you, Beth. So with that in mind, let's just kind of pick up where we left off. So like we said, standardization efforts really began to pick up in the mid 1990s, and that's where we got these different protocols that Matt just gave us a demonstration of: Modbus, DNP3, and the 6870 family of protocol. Just highlighting again what the key innovations there were. We're now doing everything over communications when it comes to everything that's transmitted between our secondary equipment, our local HMI, our gateway that's sending information off to our control center, or a historian. Around the same time, efforts began on IEC 61850. Sorry. So work first began in around the year 1995, and the standard, or the first parts of the standard, were released in 2003 and 2004. So that would have been edition 1. Today we're working on edition 2.1. And I threw in some stars here just to indicate what's new when it comes to 61850 compared to the point-based protocols that we spoke about before. The first of those things is going to be our hierarchical semantic data model. I'll unpack exactly what I mean when I say that here in a moment, but for hierarchical, think envelopes within envelopes, an organizational structure that allows us to organize our data. Semantic, that just means a way to describe things in a way that actually makes sense. We're no longer describing an address based on a data type and a point number. We now have an opportunity to describe it in ways that are both machine readable and human readable. Next, we have the 3 unique communication protocols that make up 61850. A lot of times people refer to 61850 as a communication protocol, and it's really not, or at least it's not a single one. There's 3 that are contained within it, along with these other areas that I have starred. So those 3 communication protocols are going to be GOOSE. From a high level, that's just going to replace our control wiring with communications. Sample values, again, from a high level, we'll dig into this more in a moment. That's going to replace our CT and PT wiring. We'll still have CTs and PTs, but they'll only go to a single device, and then we'll transmit those currents and voltages out at high speeds using the sample values communication protocol. And finally, client server via the MMS protocol. And this is what we're going to use for our supervisory control and data acquisition, much like we do with DNP3 and Modbus. This is the one that's most similar to those. Finally, we have our accompanying engineering process. So 6150 lays out a framework and a set of tools for specifying, designing, configuring, and even commissioning a digital substation. And that is all reliant on SCL, or the System Configuration Language. This is an XML-based language that allows us to describe the capabilities and configuration of our individual IEDs, and in turn, our substation as a whole. So we're going to begin by diving into the first of these, the hierarchical semantic data model. So pictured here on the left-hand side, I have the hierarchy, beginning with IED. So an IED is a physical device that you can hold in your hand. Intelligent Electronic Device is what it stands for. And think, in a most basic sense, either a protective relay or, as my example over here on the right, switchgear control unit, or SCU. So this will be an IED that interfaces directly with a piece of switchgear, for example, a breaker. Now moving one step down, we have our logical device. So modern IEDs commonly perform multiple functions. They're not just limited to, for example, control or protection or even supervisory functions. They might have multiple. And this is just a container that you can use to organize the different functionality of a single IED. The example that I give here is control. Moving one step further, we get into the logical node. So this is a key element and one that we'll be diving in deeper on in a moment. Logical node is just a way to functionally group data that is all centered around a single function of your substation or a single piece of maybe conducting equipment. So the example here is XCBR. X indicates that it's an interface to a piece of switchgear, and CBR stands for circuit breaker. And then within that, we'll have different data objects that relate to it. So one of those, maybe the most important one in some context, will be position. So this is the one that tells us, or at least contains the data attributes that tell us, is the breaker actually opened or closed? And then finally, we have data attribute down here at the bottom. So this is the leaf node. This is at the end of the tree for our 61850 data model. Everything is going to ultimately end with a data attribute. And the example I have here is value. So value is it's the only one that actually has any actual data within it. Everything else is just a container or a container within a container. Now, as I talked about, there's the hierarchy and there's the semantic portion of this. So when I say semantics, what I'm referring to is the ability to describe a specific data attribute by a path. So if we take our example over here, we'll see the IED, the logical device, the logical node, the data object, and finally the data attribute. This is an address that refers to a specific piece of data. Specifically, it tells us if this specific breaker is open or closed, if I was to read this exact data attribute. So just a quick word on naming conventions. So in general, and this is vary a little bit by manufacturer, but you can name your IED whatever you would like. There are some commonalities when it comes to roles. So I already mentioned SCU for switchgear control unit. There's a host of others. BCU might be bay control unit, LPU might be line protection unit, but ultimately it's up to you and your utility to come up with what names you want to use to describe your specific IEDs. Moving down, the same is true for logical devices. There are commonalities that are used across vendors, but ultimately it's up to you to come up with how you want to logically break up the functionality of your IED. So control and protection are two examples that you might break up the functionality into those two different buckets, if you will. Once we get into these next three, where I've drawn a red box, these are the three that I'll be diving in deeper on. And this is where the standardization really takes hold. So logical nodes are standardized. There's a list, and you can add a custom prefix. So that would, in the example in XCBR, you might add a prefix that indicates which breaker that function or logical node is actually interfacing with. Additionally, you might add a suffix just to indicate an instance number. Moving down to data objects and data attributes, again, these are standardized and cannot be changed. There are some caveats that we'll dig into later. There are opportunities to build custom logical nodes, but we'll cover that when we get to it. So let's take a deeper dive. What do I mean when I say logical node? It's a term that you're going to hear a lot as you continue to play in the world of 61850. And that's because it really is the fundamental building block of the 61850 data model. You can look at a logical node and know what it does once you begin to learn how to decode them. Each one represents a specific function. So for example, a protection function, you might have a pdis, or protection distance. For distance protection, pdiff, protection for the p, and then diff for differential protection. And included in the handout that we have included in this webinar, you can see a list of some of the common logical nodes. Why do we do it? Well, it's an interoperable way for us to describe the capabilities of our substation and group data within it. There are over 280 total that are defined across the standard, and that's in multiple different documents and technical reports. Over here on the right-hand side, you see just a representation of that hierarchy. You can think of it as being just another way to represent those containers that we saw on the last slide. Up here at the top, our IED, our logical device, in this case control, and then the different logical nodes within it. As I said, there are semantics to it. This table is also provided in that handout as well, and it's a way to decode what a given logical node means. So in the case of X over here, as with XCBR that I keep talking about, X is going to represent a switchgear interface. And then in this case, CBR stands for circuit breaker. Whereas XSWI, also an interface to a piece of switchgear, but in this case, it's an actual switch. If we look at our table, we see C corresponds to control. So SWI, again, this is going to be a control for a switch or potentially a breaker. So there is a little bit of getting used to and a little bit of learning the ropes, but once you begin to understand the terminology and the semantics that are used, it's extremely powerful, and you are no longer reliant on vendor-specific acronyms and a data table or data map. So our next step down, moving below logical nodes, is going to be data objects. So at the end of the day, it's really just another container. It's a way to group data attributes within a given logical node. Data attributes are standardized, and the same data object is going to be used multiple times across different logical nodes. So the example I already gave, XCBR, X for switchgear interface, CBR for circuit breaker, and XSWI, switchgear interface to a switch, those both are going to have a position shown down here. So notice my position can still be expanded out. That's because it has this little arrow over here. And that's because we haven't gotten to the bottom of the tree. And that bottom of the tree, the actual leaf node, is going to be our data attributes. Data attributes can actually be containers, but they are the only ones that cannot be containers. That can be actual leaf nodes. This is where the data or the payload actually resides. So the example, if we were to drill deeper into our position data object within our breaker logical node, we might be looking at the actual position value or the status value, in this case indicated by STVal. This is a double bit. You could have 4 possible positions, but we see that it is on. So that tells us that it's actually closed. It could also be off, intermediate, or an error condition. Other pieces of information that you'll find at this level, other data attributes inside of this position that I want to draw your attention to would be Q. This will indicate quality, and T for timestamp, telling us when the value last changed. So this is that metadata, like I spoke about before, that's associated with this point STVal or with this data object position. Much like logical nodes and data objects, these are all standardized and predefined. So now that we've covered the hierarchical semantic data model, you might be wondering, how do we actually transmit the data back and forth between our devices? One of the key takeaways that I hope you guys leave today with is that 61850 is not just a communication protocol. In fact, it's actually 3 communication protocols and everything else that we're discussing. So what are those 3 communication protocols and how are they used? That's what we'll be covering here in our next portion of the presentation. The first of the three that we'll dive into is client server. So this utilizes the MMS protocol as an underlying transport mechanism. And it's the one that's typically used for reporting information up to a SCADA system, much like DNP3 or 104, and receiving controls back down. So if an operator wants to sit at his desk and issue an open command to a specific breaker, for example, the mechanism that's going to enable that is going to be client-server communications. Likewise, if he wants to see that that breaker actually opened, that status information is going to come back via report, which is carried over this protocol. Now, GOOSE and sample values are going to be horizontal communications, and I'll define that in a moment. But these are flowing back and forth between the different pieces of secondary equipment. GOOSE is, there's really not a comparison for it in our traditional world of non-digital substations, except for control wiring. So dedicated pieces of copper that carry one signal that's either high or low, you can now do that in GOOSE. But you're not just limited to binaries. You can package really just about any data type into a GOOSE message, but it's going to be very high speed and multicast. The same is true of sample values, but in the case of sample values, we're transmitting specifically digitized measurement data. So this is an ongoing stream that allows us to reconstruct the waveform of either current or voltage. And ultimately, this serves to replace the CT and PT wiring that you're going to have in a traditional substation. So vertical versus horizontal. I spoke about this before. Vertical is what we already had. We just have a new mechanism of doing it. It's a way to carry information from our different pieces of secondary equipment. So for example, our different protective relays up to our HMI, where we can view and monitor the information, maybe an engineering laptop or a historian, or even offsite via gateway to a control center. And that's the one in 62850 that we'll use client server or MMS for. Or horizontal communications are what's new. Traditionally, this was done via wires, but now we have the opportunity to send data back and forth between the different pieces of secondary equipment using these horizontal communication protocols, specifically GOOSE and sample values, serving to replace the wiring. So now let's dig a little bit deeper into this vertical one, client server. So fundamentally, its purpose is to enable communication between those different pieces of secondary equipment and then our monitoring or SCADA infrastructure, and then have control sent back down. It does this, at least for sending data up, via the mechanism of reports. And we'll dive into how those work a little bit more. But the key takeaways here, it uses our standardized object-oriented model that we spoke about before, our semantic data model, in order to structure these data exchanges. You pick which data you want to send, put it into a data set, associate that data set with a report, and then up top, your SCADA system can subscribe to those reports. Our data sets are totally customizable. You no longer have a limited number of classes that you can put data in like you might have with DNP3. So data set, that's a term that I just mentioned, and I want to dive in a little bit deeper about what it actually means. This is something that you'll have to do if you are a system integrator or utility who's designing a substation communication system. So a data set is just an opportunity for you to pick out what data you actually want to transmit. So here on our left-hand side, we have just a single line representation of a single bay within a substation, and an IED that might be associated with some of these different pieces of conducting equipment. As I said before, XSWI, that's going to contain an interface to a piece of conducting, a piece of switchgear, in this case, an actual switch. And then within that logical node, I have a data object position. Now, typically with our client server data communications, we're going to include that entire data object into my data set. So that includes within that data object, the actual status value telling us the position of the switch, but also our quality and timestamp. Next, I'm going to associate that data set with different report control blocks on that IED. Report control block, that's just the term that we use within 62850 for an actual report that's going to be sent up to our clients. I might have other report control blocks that are associated with other data sets. This is totally configurable by you. but it's not uncommon to have one data set associated with multiple reports. And that's because this is not a multicast system like we'll be talking about in a moment. Each report control block, or at least each instance of a report control block, is associated with a single subscribing IED. So these subscribers or clients over here, to use 6150 terminology, might be a SCADA master, a local HMI, a historian, anyone that wants to consume that information from our different pieces of secondary equipment. So he will enable this report control block, and after that, anytime the data in this associated data set changes, a report will be sent from this IED up to my SCADA master containing what data changed. And Matt will demonstrate this for us in a couple moments using several different tools. Next, the second of the three communication protocols, GOOSE, standing for Generic Object-Oriented System Event. So the key takeaway here is that this is very fast, and it's the one that's used to replace copper wire transmitting inputs and outputs between the different IEDs. We're now able to do that over either fiber or traditional Ethernet, depending on your network design. When I say fast, how fast do I really mean? Well, we're talking about in the range of 3 milliseconds from the time that an event occurs until it's received and processed by the other device. Now, this is a multicast format, so a single message is sent out from the publisher, the IED that actually records the initial change from maybe a sensor, let's say, but then any devices who are configured can subscribe to that one message. It's sent out on the wire to everybody, and if you're configured to, then you can just rip it off the wire and process it. Additionally, in order for this speed to occur, there's no acknowledgement of repetition, but there are other methods of ensuring quality of service. Specifically, there's a repetition algorithm that we'll discuss more in a future webinar. So again, our key takeaway here, GOOSE allows us to replace these wires down at the bottom and send that same information over fiber up here at the top. In order to maintain reliability, as I said, there's several mechanisms built in. You might have a redundant network topology, either a ring or a star, and then GOOSE itself has that repetition. Now, much like we had with our client-server communications, we still are going to have a data set with GOOSE, but typically we're going to build our own data sets for GOOSE and not necessarily the same data set used for both. And that's because it's not always going to be the same information that we need for our protection and control algorithms as we do for our supervisory stuff. So typically when we're building a data set for GOOSE, we're going to have our status value and quality. Notice here that we drilled down to the data attribute level and we left out our timestamp. Ultimately, this is up to you as an end user to decide which of these you want to include, but the thought here is that GOOSE is so fast that we no longer really need the timestamp information because we're receiving the information within a fraction of milliseconds of when the change occurred, and the timestamp's much more useful for a historian or some other SCADA level application. Now, one key difference, I don't need to associate the same data set with multiple different GOOSE control blocks. Instead, I here have associated this data set with a single GOOSE control block because we're now using a multicast paradigm. This is in contrast to what we saw with client server. This GOOSE control block is published out on the wire, and any IEDs that are configured to subscribe to it can grab information out of that. And it's totally fair if all these IEDs don't need all of this information. You don't want your GOOSE data set to be huge, but it's fine to just have one with different pieces of information that these different IEDs will need, even if they don't need all of it. Just to illustrate this point further, I have a quick example. So let's say we again have our same single line over here on the left-hand side, and we have an IED with a data set containing the position of 4 different switches. These will be packaged up into a GOOSE message with a state number of, let's say, N-1 and transmitted out on the wire to a subscribing IED. This IED will receive that information, and in this case, this subscriber is only configured to need, let's say, or for his control operations or protection operations, he only needs 2 of these switch positions. He'll grab those off the wire, and then some short time later, let's say the breaker changes state and is now closed. This will be captured by a copper wire leading into my IED and then sent out in a subsequent message. My state number changes and it's published out on the wire, and just this change is going to be grabbed by my subscribing IED. Finally, the last of the 3 communication protocols that I want to highlight today, and that will be sampled values. So sample values is all about transmitting currents and voltages in a continuous stream from one IED to another. It's very fast, just like GOOSE, and it's also multicast, just like GOOSE. It provides synchronization mechanisms so that if you are viewing streams from multiple different IEDs that are measuring at different points in order to do maybe a differential protection, you have an opportunity to match those up and compare apples to apples across those different streams. Why do we do this? Well, it's ultimately to reduce the amount of analog wiring that we have in our substation. No longer does that CT or PT need to be wired up to multiple IEDs. I wired up to a single ID, commonly called a merging unit or process interface unit in 61850 terminology. And that one IED publishes out the sample value stream that multiple other IEDs can subscribe to without any signal degradation, regardless of how far it's transferring. So how does that actually work? Well, here I just have a quick illustration to hopefully highlight that. So in the US, we use a 60 Hertz system. So one cycle would nominally be 1/60th of a second. So in a sample value stream, typically we'll have 80 samples per period, a period being, this 1/60th of a second. And that results in every 208 milliseconds, a sample being taken. So we'll sample what point are we on the wave every 208 microseconds, I should say. And then we will package those up and send them out on a stream very, very quickly so that any subscribing IEDs can receive them, rebuild that waveform, and do any sort of protection or control algorithm that it needs. This results in, at least in a 60 Hertz system, 4,800 times per second, we are sending out a message. Now, we're not doing that uniquely or individually for each of the 3 phases plus neutral of current and voltage. We're actually going to package all of these measurements together into a single packet and send that out. So there's actually 4,800 packets that are hitting the wire, but you can multiply that by 4 in order to think of the total number of samples, because like I said, we might be measuring all 3 phases plus neutral. Now, there is the opportunity to customize the sample rate, the data set, even the number of samples for even a single phase that's packaged into a single packet. And we'll cover this in more detail when we do a deeper dive on our communication protocol webinar here in a few weeks. Again, just to see this in sort of a graphical form, we have our merging unit or process interface unit. This is it's a piece of secondary equipment. It's a type of 61850 IED that's wired up to a PT, a potential transformer, and a current transducer. Those measurements are brought into the IED and digitized and sampled, and then transmitted out at high speeds over a fiber network to any subscribing IEDs. There also will be a clock on this network that all of these devices have the opportunity to synchronize to, so that they know, again, if they're measuring or receiving measurements from multiple publishers, how they can synchronize those together and make sure that they're comparing samples from the same point in time, which will be necessary for certain types of protection. So another terminology, or a piece of terminology that comes up a lot when we talk about sample values, is the term process bus. Just want to quickly define what that is. It's not a term that actually appears as part of the standard, but it's a term that the industry as a whole has widely adopted. And the other companion term to that is station bus. So I quickly just want to define, what do people mean when you hear these terms? They're not actually that complicated. So when you hear process bus, the easiest way to describe it is think sample values, or more specifically, the network where the sample values will flow. GOOSE commonly will also be on this as well, although it can also be on my station bus as well. So my different IEDs that are interfacing directly with the switchgear, or the IEDs that are interfacing directly with the CTs or PTs, will transmit GOOSE and sample values over a dedicated network up to the IEDs that need to consume that information. These are all just different IEDs that are different pieces of secondary equipment. Now, you'll notice these IEDs in the middle are actually straddling both the station bus and the process bus. Typically, these will have multiple network interfaces, one facing the process bus side and another one facing the station bus side. Our station bus still might contain GOOSE messages that are transmitted horizontally between these different IEDs, but crucially, it will also contain the client-server communication, the reports that are being sent from these different IEDs up to my SCADA system, my HMI, my control center, my gateway, my historian. So again, don't get confused if you hear these terms process bus and station bus. They're commonly used together in the same substation. When you hear process bus, think inclusion of sample values and a dedicated network to do that. With that, I'm going to go ahead and pause and turn it back over to Matt, who will be using Distributed Test Manager as well as Test Suite Pro in order to demonstrate some of these concepts. Visualize data models, we'll have client server reports, as well as GOOSE messaging, going back and forth and visualizing all of these. Thanks.
Okay, Matt, you're the organizer now. You're on mute.
All right, everyone should be able to see my screen again. So we are back in the DTM application right now. The reason I wanted to point this out was to allude to a little bit of what Jackson said about the SCL files. As you may have noticed, the amount of devices in this workspace for 61850 greatly outnumbers the 2 devices we were looking in the other protocols. And that's because this workspace was originally primarily set up as a 61850 workspace. And sure, you can come in and add all of the 61850 devices individually, but if you have a properly formatted SCD file, which is a full substation worth of devices, communication sections, substation sections, all of that's completely filled out, you can actually come in and pull in the SCD and all of the devices at once in two different ways. You can go into import IEDs from SCD, and this will allow you to bring in and pick and choose. I want, this one, that one, and maybe the 5th one, and bring those in. That way you can have some simulated devices and some physical devices working in tandem together. And so maybe you haven't been properly shipped the device you ordered, or you're still testing out a theory or whatever. You might do that. You can also do import substation wizard. This will allow you to bring that SCD file and build up a workspace such as the one you're seeing here almost automatically. It'll go through, like I said, the substation, communications, the IED section, add all of your devices. It'll try to build up a single line diagram for you. And it'll even start layering some of the the commonly used protection schemes and behavioral stuff on top of it. So that's how this workspace was built up. Like with the last demonstration that I did, I'm going to go ahead and activate a auto data change for the exact same manner as before, just so we have something changing. Specifically, this one is just going to be a voltage level. It's just going to be moving back and forth in a sinusoidal wave here between these two values. That way I can generate event data and I can actually monitor points changing in the device. So I'm going to go ahead and start that up. It is worth noting that the voltage that I am changing is used in a report control blocks data set and not necessarily in a GOOSE control blocks data set. And we'll dive a little bit deeper for the ramifications for that once we get over to our Test Suite Pro tool. So let's go ahead and bring up Test Suite Pro. This is what it looks like. It is built off the same SCL file that your DTM workspace is, or the ones that you would create during your engineering process. So I provided the exact same SCD file to Test Suite Pro, and we're simulating all of these devices as clients to connect up to all of the devices in the DTM simulation or the physical devices. So let's go ahead and take a look at the model, and we can do that through the advanced client. Then you can choose whichever device you're interested in. So out of all devices, I'm taking a look at D1 line 2 BCU. Jackson mentioned earlier that it's containers with containers, right? So we have this diagram here he was talking about. You start at your IED, You've got your logical device, logical nodes, data objects, data attribute, potentially nested data attributes, and then your final value at the bottom. Well, that's what we're going to be looking at right here in this model. So we have our IED, that's our D1 line 2 BCU, and that's broken up into multiple logical devices. And so we can take a look at what these logical devices are. Well, it's just the same string as before. D1, that's a voltage level. Line 2, that's the second line on it. BCU, that's the bay controller unit. And then our logical devices have been broken up between measurements and controls. So if I open up the measurements, we'll be able to see the logical nodes inside. We've got LLN0, that is a required logical node to give some metadata based on the device and its capabilities. We've got LPHD and some LGOS. This helps with GOOSE. And then we've got MMXU. The MMXU holds all of the measurement values, which makes sense because this logical node is inside of a measurement logical device. We can open that up, and now we have access to data objects. So I can go in, I think the value that I said was changing before was a voltage. So I can go into this voltage data object here. There's phase A. Then we've got broken up here is the timestamp, that's T. The quality is here, it's good. And then we can drill down to the value, the magnitude of the value. And sure enough, here is what we have. So just like in Modbus and just like in DNP3, we can just do polls, we can do reads. You can right click on the point you're interested in and perform a read there. You'll see the value next to it, this little icon has changed to a P, and that's related to polling or reads. So you can actually see how the values are coming across to Test Suite Pro based on this table up here. And just like before, periodically, I could individually click this and get that value. But just like previously, if you're just periodically pulling data, you might miss something. So we have the concept of reports in Test Suite Pro and 61850, and you can see that inside of the metadata logical node LLN0. So I'll open this up, and like I said, you have nameplate information, some behavioral, some mode, things like that. But I'm going to be looking at these top three, the report control block and the GOOSE control block. The report control block here is BRCB 101. That seems like just a bunch of letters, but we tried to make it named in such a way it can help the engineer interacting with it. So BRCB is buffered report control block, whereas the GCB, the GOOSE control block, was named GCB. Then if I opened up this buffered report control block, you'll be able to see all of the attributes associated with that. More specifically, though, I'm going to be looking at this data set value here. And this data set is being used as the DS underscore BRCB1. So I can go into that by going into the data sets. Here's our DS BRCB1. That is just our buffered report control block, and DS stands for data set. I can open that up, and here's all the values that we're supplying. You'll notice some of these. I've got amps and amps on phase A, amps on phase B, amps on phase C, hertz, voltages, right? These are all the measurement values I was kind of playing with before. Matter of fact, you can even, instead of needing to follow each of these little lines, you can right click and do locate. But what makes this a little more useful in the semantic model rather than just kind of a flat, I hope you have your Excel mapping sheet, is you can actually walk down the line of this. So like I did before with the device, we've got D1, the voltage, line 2, a bay controller unit, measurement values, amps, and that's the amps at phase A. So even if you just have a value next to the name of the point, you can already have a lot more contextual information about that point. So I know what the data set is and all the attributes and data objects within that data set, and I know that data set is being used within this buffered report control block. So now, like we can enable unsolicited messages, I can actually right click here and enable report control blocks. Now you'll see it has turned green. And if I scroll back down to my magnitude here, you'll see that the icon has changed from that P, because when I pulled it, to a bar graph, which represents by reporting. Now, without doing any sort of periodic reads or polling or anything, we're seeing these values update as they update in our simulation or on our physical device. You can also check out historical data for this in Test Suite Pro. This is a feature that we've added specifically so people can look back at what happened, not just the current state of things. So right now, all we can see is what the value is currently, and that's over here in one of our tools. We have a whole section over here for displays as well. And so if I go to the report viewer here, we'll see we have about 100 reports being stored up here. I have a setting in Test Suite Pro that it only remembers the last 100 or so reports. So technically there should be more if you set that to higher. But you can basically go in and check one of these reports and see what the values are inside of that report. So when this came across the line, the magnitude is the only thing that really changed in here, and the voltage was this number. Or you could go to the next one and see, well, this reason this report came in is data change, and sure enough, the voltage has changed. You can even come in here and multi-select and grab a bunch of these and actually look at them side by side, and it will highlight the differences between the events and let you know, obviously the timestamp is going to keep incrementing, the quality is not changing, but some of the values are. So you can get a historical approach. Now, you could do the exact same thing I just did, but with GOOSE, right? I can come in here and right click and enable and subscribe to a GOOSE control block. And just like the report viewer, we do have a GOOSE viewer. But I want to make sure I really emphasize the difference here between GOOSE and reports. GOOSE is very typically peer-to-peer, server-to-server, all done at that level. It's not normally between a server and a client. But Test Suite Pro is a testing tool, and sometimes you'll need to know what the server is goosing out or sending out as a GOOSE message to its peers and who's subscribing to it. So instead of bringing up a simulated server and adding some inputs to it and subscribing to GOOSE that way, we do allow you to subscribe to GOOSE in Test Suite Pro, but that's solely for the intent to be able to get that data and see what other devices in your network should be seeing from your device. Now, if I go into the GOOSE control block here, we'll see the data set is not the same one as we were looking at before. This is the DS dataset _ GCB, that's the GOOSE control block. And when I open this up, we'll see it's a lot more operational stuff. We've got our op close.general and the quality. We've got an op open, general and quality, but we're not seeing our voltages and currents in here. So because of that, if I go back to my displays and I go to the the GOOSE viewer instead, while we will have a GOOSE when I have changed the value, we aren't seeing like continuous flow of data here. So what I can do is I can clear all of this and I can go over to my simulation again and maybe just like open and close a breaker that will trigger the opens and the closes that will trigger some values to be changing as part of that GOOSE control block. And when I go back to Test Suite Pro now, we'll see that we do have some values coming across the line. And just like before, you can click them, you can scroll through, you can see what changes from event to event, and actually get a kind of a layout of what historical information that you've gotten from your events that you've triggered in your simulation or on your physical devices. So now let's look at some of the more advanced features within Test Suite Pro to look at your 61850 environment. So we've obviously can do everything that we can do in DNP within Test Harness, but there's a few other things that we do, and some of them happen automatically for you. Number one, we have the system status over here in the tools section. This gives you an overview to let you know if the devices that you've provided the SCD file are actually out there, right? If you're saying, I want to run commands and controls on this certain server, and that server isn't powered on or isn't plugged into the network or something, your more thorough tests are going to be giving you bad data from the get-go because you can't connect to them. So the very first thing you want to know to be able to do is make sure that Test Suite Pro can interact with any of the servers that you need it to be. So I can see here that all of these have the connection status as connected. I can also see what IP address that they're communicating on. And if we're using GOOSE, what GOOSE adapter I'm actually going to be listening to for that broadcasted data. So seeing all of these green and getting a little green check mark, that gives you one quick sanity test. This happens for you kind of automatically when you start up the workspace. The next thing we're going to do is we're going to look at this compare model. So 61850 has a concept of discovery. And what that means is when you provide a server the capabilities and the model, it hosts that within itself. A client can reach out in two ways. One, you can supply the client with that same model, with that same SCL file, and then the client already knows what the server's going to be talking to and everything about that server. Or if you have a client without that file, the client can reach out and perform discovery, which is basically asking the server, hey, tell me everything about yourself. Tell me your capabilities and your model, and I'll mirror that here on me. Well, we're using that functionality to run a validation test automatically for you. So we've provided the SCD file to Test Suite Pro, so Test Suite Pro knows what the server should look like. Then it's going to go out and do a discovery on the server and match, I know what you should look like, what do you actually look like, and make sure that they're a match. If they're not, it'll report a warning or error. It'll, instead of being green here, you'll see a yellow for a warning or a red for an error. You can, drill down and see where the difference is, and we'll also give you a description of what we expected and what we actually saw here. So similar to the compare model tool, looking and saying, I know what should be there, and here's what's actually there. That's what the Goose tracker does for Goose. So we provided an SCD file to Test Suite Pro, and inside of that SCD file, we said there should be 17 streams of Goose. Here's their names, here's their data sets, here's all the information about them. Well, Test Suite Pro is first going to go out and sniff the wire and say, are they there? If someone, forgot to configure Goose on a device, or maybe they're not plugged into the network, or the device isn't powered on, or whatever, it might say that there are devices missing on wire. And you can actually go and mouse over each of these column headers here to see what you could see as what we are checking for errors. For instance, missing on wire would be a stream warning. You told me that there should be a stream. I'm not seeing that stream. It's missing. Another possible error that you might see on this column here is missing an SCL. So maybe in a previous iteration of your design scheme, you had 18 Goose streams instead of 17. You made some updates to the SCL file. You realize one of them could be, the information could be gained in a more simple way, and you just cut one of the devices. Well, you forgot to power off that device, and when Test Suite Pro starts up, it says, hey, I see the 17 you told me that should be here, but there's this one weird guy, and I don't know what that is. I just want you to know about it. I sniffed it out, and here it is, and you can see the information on it. So we're seeing all of those here as valid. What you might notice is there actually is one in here for a stream warning. So I can go over here to this status, and it can give me some information. This status column is just kind of a conglomeration of all of the other columns and letting you know what possibly could be seen across all of our tests here. If I mouse over this one, it'll let me know that it found a stream and a simulated reserve flag is set. And you can see that in this column here. Essentially what that means is that there is like a test set out there somewhere, and that's publishing Goose, but it's publishing it in a mode that is specifically designed to test a device without necessarily impacting the rest of the devices that aren't set up to operate in that mode. And I specifically put this out here for two purposes. One, to show off the functionality of the Goose tracker, but also to show off some functionality of the LGOS later on. This stream here is actually being published by Test Suite Pro. I can go to the Goose Publisher tool here, and if you give a adapter here for where the Goose should be published out of and broadcasted on, you can actually go in and run any of these streams. Again, Test Suite Pro has been provided the SCD file, so it knows what the stream should look like, so it knows how to mimic that stream. That way you don't have to have all the physical devices, or you don't have to spin up a server to actually get initial conditions or something set. So I have this LPU control being broadcast here through Test Suite Pro as an addition to the actual one that's being broadcast in DTM. So that's how the Goose tracker works. We can move on to the LGOS tool. The LGOS tool is a tool that allows us as the client application to see the status of how the servers are communicating with each other. So the rows seen here on the left are the Goose streams, and it's just like you would see in the Goose tracker. whereas the columns here along the top are all of the IEDs that could possibly subscribe to those streams. And then if you mouse over a cell where these overlap, you can see the information that is reported by the IED to Test Suite Pro. And this is based on the subscription status. It's broken up into 3 different sections. As you can see, the top section here is the current status of the connection. So you'll see it's in a normal situation. The text reads, subscriber is configured to receive normal GOOSE, and it is receiving them. So we know the server is expecting to receive this GOOSE stream, and that server is getting the GOOSE stream. It's good to go. The second section here is DAs in the group stream consumed by the ID. That means the data attributes within that GOOSE stream that are used. I think you saw earlier, Jackson was saying you can pick and choose the attributes out of the stream that are relevant to you. Well, specifically, this one is interested in this general and the quality of that general there. And so you can actually go through and check all of the values here and where they're actually being pulled in. And finally, you can see the LGOS system status here. It gives you a quick summary over the status of the stream as a whole and gives you some additional information. So we've got some warnings here on this test subscriber out here, which is this kind of burgundy color. And sure, you can mouse over the burgundy color and get a little bit of a tooltip, or you can take a look at the table here and just see. So this test subscriber is subscribed, but there's no LGOS. If there's no LGOS logical node, then there's no way for us to pull the metadata around the GOOSE subscription. So that's not necessarily an error, that's just a warning, and that's how you can kind of quickly see it. You might also notice that we have one stream and one device that are highlighted in yellow here. And this is what I was talking about while we were publishing a stream with that simulate bit checked. This is part of the process of doing something that 61850 calls virtual isolation. It allows you to take a device in a pre-configured network and basically isolate them away from the rest of the environment. It's going to say, hey, listen to my test signals, respond with test signals, interact with me, and let the rest of the network continue to do their thing. That way you don't have to go and rip out connection wires or unplug things or de-rack devices. You can just set it in this specific mode to allow you to run and execute tests on it without necessarily popping breakers or sending GOOSE streams out to other devices that are subscribed to your data that could potentially be misleading to them. So this one specific device, when it comes to this stream, is in a test mode right now. So now that we've done all of these are all run automatically for you when you first open Test Suite Pro. Typically, if everything's running properly, you don't even have to worry about looking at these. But if for some reason there is an issue, we will try to report that to you automatically, because it's better to find out now that there is some foundational issue, whether it's a missing GOOSE signal, missing device, or whatever, before you get into your more thorough tests and you run your more system-wide tests and realize some of the data you might have gotten is bad. So once we pass all of those kind of sanity tests, we can then go over to the displays. So we've already seen 2 displays. We've seen the GOOSE viewer and the report viewer here. That's the historical view of the data that we've already seen, but we have a few more I want to show off during this presentation today. For instance, we have the custom display. The custom display is, like we saw here, a single line diagram. Now you can set this up and just have values. You can really build up the custom display however you want. And you might say, isn't this a little redundant? I've seen the single line diagram over in DTM. I've gotten that question actually a few times. And the response to it is, yes, if you're using DTM and Test Suite Pro and you have a single line diagram in both, there might be some overlap there. But a real world situation generally has some physical IDs, or after commissioning, you might be in maintenance and there are no simulated IDs, right? So you walk into a substation, you plug Test Suite Pro in, now you have access to a visual interface that you might not have in other ways. So just to show this off a little bit, if I go back over to DTM and I say, toggle this breaker here, it sends out the GOOSE message, it sends out any information related to that, and sure enough, that breaker is updated. You'll also see that this is line 2, like we've been looking at today, and it is highlighted yellow, just like the LGOS. That's because the IED that is set for the simulated stream is giving values based on the switch positions here. So it's been shown in the single line diagram. Whereas the other three here are just in a nominal state looking at the real streams going across the line. And you can build these up just by dragging things in or grabbing attributes and dragging them in. You can see the currents along the lines and the voltages. You can really set these up as however you want, or even have multiple different displays here. The next thing I'm going to take a look at is the signal flow. So the signal flow allows you to track how data is flowing around your network. So you can see here we've got our D1 line 1 LPU. That is one of our IEDs, and inside of our IEDs we have our dark blue squares. These are our logical devices. So we've got a prot, that's protection, and control, as we've seen before. And so any sort of line staying inside of this light blue is all internal communication and logic, whereas anything that comes out from the light blue from one IED to another, that will be done by GOOSE. So why would you need something like this? I mean, we can see the individual values, we can go to the advanced clients and drill down. Well, the reason you might want something like this is because in a circumstance when you're doing like a protection scheme, a lot of things can happen all at once and you can't be monitoring them all at once. So for instance, I have a bunch of buttons here that will enact certain different states on the electrical equipment. For instance, this first button up here is a differential fault, so pdiff. I can create a differential fault on line 1 by clicking this button. And what should happen in that case is the breaker should be opened, right? There's a fault on the line, we should open it up. Sometimes just by simply opening the breaker and closing the breaker, the fault is taken care of. And in that case, the breaker can then just close back and remain closed and everything is back to its nominal state. Other times, if it closes back and the fault's still there, it needs to open again and then signal someone to come actually take a look at what's causing this fault. You can generate a permanent versus temporary fault with this little green checkbox here. I'm going to leave it green, saying that it is a temporary fault. And if I click this button, the breaker will open and then it'll close like I described, and that's that. And if this was, a very simple simulation, this button literally could just move that breaker open and close. But it's not. It's simulating some of the electrical and all of the protocol stuff and the protection scheme that's going on behind the scenes. So a lot of GOOSE messages were sent, potentially some reports were triggered, but we didn't see any of that. If you go into Test Suite Pro and you go back to your signal flow, you can click record here. It's going to go out and grab all the initial conditions of everything, and it's just going to wait for events to come across. So now when I go back and trigger that exact same fault, the breaker open and then the breaker will close, and go to Test Suite Pro, we'll see we've recorded a bunch of different events. Let me go ahead and stop that, the recording. So now I've got these events on a timeline here, and I could just play them back and it could all happen, but I like to step through them one at a time. So I'll go to this button here and click the first. Well, the first thing that happens is the differential fault sent a signal to the PTRC. The PTRC kind of multiplexes a bunch of possible options to cause a trip to happen and basically says, if any of the situations go true where I should open the breaker and send a trip signal, I'll just send that for them. So it notices there's a differential fault. The next thing it does, you can see it's sending a GOOSE message out to our line 1 SCU here. And that has the ability to actually open the breaker. And sure enough, the breaker's position changes. When the breaker position changes, it sends out a GOOSE message to several different places, including the CSWI. So Jackson mentioned that earlier. That's the controllable switch. This is the BCU controllable switch. So that is the bay controller unit. It also let the recloser know, hey, the breaker's open. So if you need to do your reclosing thing, do it. You can continue to step through. The fault then goes low, right? The PTRC goes back low with its falling edge. The recloser says, hey, I noticed the breaker open. Let's try to close it. So the position triggered the op close. The op close then went to the bay controller unit, which then sent an op close back to the breaker. And sure enough, the breaker then closed. So you can really step through each individual step of the simulation or your physical device to make sure things are working properly. Let's say the breaker opened and it never closed. it could be possible that maybe the line between the recloser and the bay controller unit, maybe it's not goosing properly, so you wouldn't actually be able to see the transfer of data here, and you're like, well, the recloser did its job, but the signal flow did not show the recloser actually transmitting that up to the bay controller unit. We can look at this event in a different way. We can look at it from the logic analyzer. So I've taken some of the data attributes from the previous signal flow and put them in a list. So we've got our differential fault, our trip.general from our PTRC, our XCBR, and our recloser. And I can click record here, and we'll go ahead and get those values again. And if I go back and I trigger the same event, just open and then close, we can see it more in a timing way. So if I click stop, I can start to zoom in a little bit, and we can see the rising edge and falling edge, kind of similar to how Jackson was showing off in his demonstration. So you can come over here to the cursors, and maybe like one of your spec requirements is we need to have a certain time between when the fault's detected and the breaker actually opens. So you can grab these cursors and set them. Okay, I'll put this to the rising edge of the PDIF. That's when the fault is detected. And then the falling edge of the XCBR is when the breaker actually opened. So I'll match that there, and we'll see it's about half a second. Is that good enough? Great. If it's not, you can investigate things even further. Well, the breaker opened, you know, within about basically 80% of the time took for the breaker to open from the PTRC. So maybe we could speed that up a little bit. Or maybe if something was really wrong, you could see the P differential triggered way over here, but the PTRC only triggered here, right? And so you could say, oh, wow, something's definitely timing-wise going wrong between our differential fault detection and the trip general being sent. So you can validate your performance through the signal flow and the logic analyzer with timing. And after you do all of that and you're happy with what you see, you can actually set this up as a regression test. You just come down here and you can say send a test sequencer as steps. And what that'll do is it will build up a automated test for you here. So we have a list of automated tests, recloser operations, test control operation, versatile isolations, right? You can have a full list of regression tests here, and it's broken up into individual steps, and those steps are based on the signal flow or wherever you sent the test from, right? Now you can actually go into them individually and make changes to them, set things to be to validate the order or allow them to happen, you know, out of order, depending on what your test really needs. You've got a visual representation of the test flows as well as the, you know, step 1, step 1.1, 1.2. You can step through that. You can drag user actions in here. So go check an LED is on, make sure the device is connected. You can obviously do 61850 related things, connected devices, disconnect devices, enable and disable GOOSE, report control blocks. All sorts of functionality can be built into this. So once you have everything set up in your network correctly, you can run these automated tests before commissioning, you know, in the substation or during your maintenance phase. Even if you started out building these regression tests on the simulation, you can easily migrate them to your physical devices out into the field. So I appreciate everyone's time looking at some of our applications and going over some of the concepts such as just polling and reading, report control blocks, GOOSE control blocks. We didn't get too much into sampled values yet, but that will be a topic for one of our future webinars. So hopefully we'll see you there. I'm going to pass it back over to Jackson for one last time and let him finish up the demonstration or presentation.
Okay, Jackson, you should have the screen.
All right, thank you very much. So to close out, we're going to focus on the engineering process and SCL. Beginning first with the engineering process. So as I mentioned before, 61850 has a couple different parts. The communication protocols being one of them and possibly the most famous, the semantic hierarchical data model that we already talked about, and finally the engineering process, and I'll lump SCL in there as well. So 61850 doesn't define you know, an exact structure. It really just provides a framework and a set of tools that you're able to use in order to design your system. That includes various stages, such as the specification stage, where you can lay out your single line diagram and describe the functional requirements of your system. Ultimately, that is optional. What's not optional is eventually you're going to need to choose your IEDs, the devices that you actually want to perform the different tasks within your substation. Once you have those IEDs, each one of them will have a file that describes the capabilities of it. This is commonly referred to as an ICD or IED capability description. These IEDs in the specification will be loaded into a system configuration tool. In fact, you can even do your specification in this tool. So an example of this would be HELinks, and I'll show some screenshots from that in a moment. This is a critical tool in your 61850 process. There's vendor neutral tools like HELinks that we'll be talking about that can work with any vendor's IEDs, or if you're all just choosing IEDs from a single vendor, a lot of different vendors have their own that only work with their own IEDs. But you'll spend a lot of time in this tool because it's where you're going to be configuring all of the signal exchange, all these GOOSE messages that we've talked about, configuring the data sets for those, same thing for your reports, the data sets that you want to pick out which data you actually want to transfer up to your HMI. This is also where you'll do all of your configuration of communications, right? So setting your IP addresses, VLANs, and things like that. And the output of that, as Matt already alluded to, is going to be an SCD file. And there is a description in the handout that's available with this webinar that describes some of the common different SCL file formats and what they are. So that SCD file is very important. It's going to contain the consolidated description of all of your IEDs, their functionalities, their capabilities, and all the signal exchange and communication information. This will be used to actually configure your IEDs. Finally, the last step is going to be implementation and testing. And this is another area where Triangle tools really come in handy. So here I have a slide just kind of with a high level overview of the engineering process, specifically highlighting where Triangle's different tools fit in. So we begin here not so much with the specification, but with our different IED capability files or ICDs. You're able to validate those or even create ICDs with the tool that I'll be showing in a moment, SCL Navigator, which is an SCL viewer. You're going to load these into your system configuration tool right here. And then that's, like I said, where a bulk of your time will be spent designing your actual system. Now, modern tools include, particularly HELinks, include the ability to design templates and reuse a lot of the information or design that you have from one substation to the next. You can really templatize as far as you'd like. The output of this, like I said, will be an SCD file that can be validated really anytime you have an SCL file using SCL Navigator. But eventually that SCL file will be pushed onto IEDs. Before you do that, you can load it into DTM as Matt has done and simulate your entire substation, not just from a communications perspective, sending GOOSE messages and reports and even sample values, but also it can be used to simulate the functionality of your substation. And we'll dive into that more in a future webinar, but it's really a very powerful feature. Finally, we have Test Suite Pro over here on the right-hand side. Initially, that can be used to create a series of tests, as Matt demonstrated, that you're running against your physical IEDs. But once you move into the factory acceptance stage, maybe you have one of your lineups of different pieces of switchgear. You might have some physical IEDs present, but not all. You can use DTM to simulate the remaining IEDs and their functionality and continue your testing. And then finally, as you move into the commissioning stage and then an ongoing maintenance, Test Suite Pro is a tool that you'll bring into the substation in order to validate those IEDs, confirm their functionality, perform virtual isolation, and the like. So I keep talking about SCL, or System Configuration Language, but what is it? Well, it's a machine-readable XML file format that was actually developed as part of 61850. And it's used to facilitate the exchange of information, specifically configurations of the different IEDs. And because it's standardized, it can go between different vendors' tools. You know, every vendor out there has their own file format for, configurations or firmware for their specific IEDs. But this is a way to standardize the parts that are related to 61850 so that everyone can use them. As I've said, you can describe system specification, your device configurations, and all of your communication settings, all in this common file format. And that's kind of a good segue into what are the different parts of an SCL file. So these are the different parts that you can have, and not every file will necessarily contain all of them, although most will. The one that you might see left out is really going to be the substation section at the top, because that applies as we move later on in the process. So that's where we're going to contain our specification. The single line diagram that we might design as part of our specification stage will be contained in there, and then a high level capability of all the functionality that we desire. A lot of work has gone into the specification stage, and really as far as you want to go with specification, you can, given some of the recent additions that have come in as part of the standard. If you guys have any questions about that, I encourage you to go ahead and take your time now and ask them, and we have several experts on the line that are happy to address that. The next section down will be the communication section, and this will be found regardless of the type of, well, just about regardless of the type of SEL file that you're looking at. This contains the IP addresses, the VLAN IDs, all that communication related information. And finally, we have our IED section. This is where we have the capabilities and configurations of all the different IEDs that make up our substation. So like I talked about before, the data models, that's where this is going to be found for the different IEDs, as well as the signal exchange information. So all the GOOSE data sets and GOOSE control blocks, our report data sets, our report control blocks, same thing for sample values. That's all going to be contained here in our IED section. And then finally, maybe the most abstract is going to be the data template section down at the bottom. So as I mentioned before, logical nodes and data objects and even data attributes are standardized. So we're going to see the same data objects and logical nodes used across multiple IEDs, even across different vendors. So the data template section gives us an opportunity to define the data structure once, and then they can just be used or referenced up in our IED section. Now in lieu of a demo, I just have a couple quick screenshots to walk us through the engineering process using the tool Helix STS. Beginning with the specification stage, we start out by designing our single line diagram, which is what we see here. We pick the different pieces of conducting equipment and choose how they're going to be connected. From there, we begin to define the functionality of our substation. So here we have several different functions. One function might have multiple logical nodes within it. And at a later time, we're actually going to associate these different pieces of functionality with different IEDs, as we've done here. Once we have our functionality defined, we have the opportunity to actually lay out the application or signal flow that'll be happening. So here we're just designing, this is ultimately going to result in a GOOSE message. When I say that you need to design your GOOSE data sets and design your GOOSE control blocks, you're not going to need to do that in SCL. It's going to be GUI driven, especially in a tool like Helix. So here we're just indicating that an operate signal is flowing from a distance protection function over to a tripping function. So this is what's actually going to cause the breaker to trip, or one piece in the puzzle that's going to cause the breaker to trip when a distance protection fault is picked up. This will be placed into a data set automatically for us, and that data set will be associated with a GOOSE control block on a publisher, and ultimately a subscriber as well will have an external reference telling it that it needs to subscribe. Finally, at least if we're following the more top-down paradigm, we're going to pick out our IEDs. So once we pick a manufacturer and a specific IED model, we're going to load in the ICD, or the IED capability description that vendor is going to provide us, or that we might export from their tool. These will be loaded into our system configuration tool as we've done here, and then we have the opportunity to associate them with functions, in different roles within our substation, and we also have the opportunity to assign the communication parameters. So, for example, here we see the different IEDs. Here we just have a single network, but if we had multiple subnets, that could also be set up here. And lastly, today we'll end with a quick look at SEL Navigator, so we can actually peer into an SEL file. As I said before, the output of our system engineering process is going to be an SCD, or System Configuration Description file. So we'll take a look at what that looks like. So the tool that you see over here on the left-hand side is actually going to be SCL Navigator. SCL, System Configuration Language Navigator, because this is a way not just to create ICD files or other forms of SCL files, but view them, edit them, and even validate them. There's a set of rules that have been defined as part of the standard that describe how, what parameters are required for a given object within a 61850 data model, and that can all be validated here within the tool. Make sure that your file is compliant. But I want to highlight the different sections over here. I just have a screenshot of the slide that we looked at a moment ago, and beginning with the substation section. So as I said, this is going to contain initially your specification. Your specification might contain a voltage level, different bays indicated here, and then your different bays will have different pieces of conducting equipment. So for example, a CBR or circuit breaker. You can also contain your functions here and even applications that will ultimately be linked to pieces of logical nodes or the like down in the IED section. After the substation section, we have our communication section. And as I said, here we can define everything that has to do with the communications of our substation. So in this particular one, we just have a single subnet and then different access points on the different IEDs. If I drill down within one of them, I can see the different communication parameters, for example, IP address or other stack, low-level settings that allow and enable the communications. Next, we move down to our IEDs. So we'll notice that there's not just one, but multiple IEDs in a typical substation. If this was an ICD file, describing the capabilities of a single IED, we would just have one IED in the section. But because this is describing a whole substation, we're going to have multiple. If I open up my IED, I'll see several different parts. But if I pick one access point, you can think of this as a physical NIC or Ethernet or fiber interface on that device. I can open that up. I'll find a 61850 server inside of it, all of the different logical devices. This is where we begin to see that hierarchy that I've been discussing. So here we can see a protection logical device, for example. We expect to find all of our protection related logical nodes within it. So for example, PDIS, P for protection, DIS for distance, and then 1 indicating the instance number. I can expand that out and see the different data objects, and then finally the different data attributes within it. Now, keep in mind, as I said, lots of times we'll have the same logical node defined multiple times. We don't need to lay out the whole definition for the logical node here in the IED section. That's actually the role of the data template section down here at the bottom. So, there's going to be a lot of data down here in the data template section. We're not going to spend much time looking through it. Just keep in mind that this is a place for us to define each logical node or even down to the data attribute level, define it once, and then we can reuse it and reference it up here in the IED section. But every data object contained within a logical node will be defined down here, including each data attribute within that. So with that, that really concludes our presentation. And so I'm going to turn it back over to, well, actually I have one or two more slides. So here I just have what I hope are our key takeaways here today for 61850. I hope you guys leave today knowing what 61850 is and what it's not. It is a hierarchical semantic data model, and as we've discussed what that means, it's a list of containers, turtles all the way down, our IED at top, logical device, logical node, data object, and data attribute, or leaf node. And this serves to replace the pointless model that we spoke about with those previous protocols, with an opportunity to organize and describe things in a hierarchical and semantic way. It's not one communication protocol, but it's really 3, used for different functions or applications within the substation. GOOSE to replace the control wiring flowing back and forth between our different pieces of secondary equipment, different IEDs. Sample values, so we still have our CTs and PTs. I saw that was one of the questions that came in, but they just come into a single device, a merging unit or a process interface unit, and then any other devices, for example, a protective relay that needs that information can subscribe to that sample value stream and do its job. And then finally, our client server or MMS communication protocol, and that's used for transmitting reports up to our SCADA system and then receiving controls back down. Lastly, the last part of the 61850 standard is going to be our engineering process, which we've just discussed. That includes the various stages, specification, design, configuration, and commissioning. And those are all made possible by use of our SCL, or System Configuration Language. And with that, I'll turn it back over to you, Beth. Thank you very much, everybody.
Okay, thanks, Jackson. Well, okay, so just to wrap up, are you guys able to see my slides?
Not yet.
Let me share my screen here.
You're good.
Oh, perfect. You can see it now?
Yep.
Okay, well, just to wrap up, so thank you everyone for staying on with us. We covered a lot of material today. You definitely saw a lot of our different tools in action as well. So appreciate so many of you stayed on for the full 2 hours, and we did get a lot of great questions in. I think some are still being answered as we wrap up, so hang on, we are still continuing to answer through a couple of those. I do want to wrap up with a couple of final thoughts. A lot of folks have asked online, how do I get the slides? So when you do leave the webinar, when I end the webinar, you will be prompted for a survey. It's only 3 questions. If you fill out the survey, you can request getting a copy to these slides. I'll send you a follow-up that will include the slides, will include the 6150 handout reference document. And if you'd like, again, answer on the survey, some additional information on the products that you've seen here. You can also request to sign up for notifications specific to this training series. If you'd like to continue to be notified of the next 6150 training modules, please also note that in the survey, and you'll receive those communications directly from me. A recording of this video will be posted onto our website in the next couple of days, so you should receive a link with the recording, but if for some reason you missed that, it could go to our website to see it there. And of course, anyone that has any questions about what you've seen here today, please email sales@trianglemicroworks.com. I'm happy to set up a follow-up meeting to go through any of your questions that you might have on what you've seen here today. We can set up any demos of the products that you've seen here as well. So please feel free to reach out with that. So on that note, we are done with the material we wanted to cover today. Like I said, there's a tremendous amount of questions that have come in, but I do have several questions here that are a little bit, I think, more general that will be beneficial for the group. So why don't we just start to go over a couple of those while the folks still continue to answer the questions online. So Matt and Jackson, I'll send these questions over to you, and we can always pull in Christoph if needed. First question is, why would you use GOOSE over sample values?
Well, I'll take a stab at that. Matt, feel free to jump in. In general, I would say that they just have 2 different roles, right? So GOOSE is going to replace the communications that were typically done, or the signal exchange that was typically done over a wire. So it's not limited to a binary, like you would in a wire, where you can just send an on or an off. But you can send analog values as well, or double bits, things like that. But it's going to be that exchange between the different pieces of secondary equipment that's necessary for, let's say, in general control functionality. Sample values, on the other hand, is going to be, I don't want to say strictly limited, because there are exceptions to the rule as always, but it's going to be currents and voltages that you're transmitting at very high speeds so that you can recreate that waveform on a subscribing device that's typically going to be necessary for a protection algorithm.
Okay. Another question that I received multiple questions on is, where can you get a hold of these tools so you can play around with them? So if you go to our website, you can download evaluations to any of the tools that you've seen here today, in addition to the other tools that we offer. You simply set up an account on our website. You'll get access to a 21-day eval. If you are working on a virtual machine, please email sales@trianglemicroworks.com, and we will send you a 21-day temporary key to apply to activate your virtual machine. So everything you've seen here is available to download an evaluation license for and try out yourself. And then, as I mentioned, we can always set up a demo and walk you through the tool as well.
To piggyback on that a little bit, the workspaces that we showed off today are actually sample workspaces we provide with both Test Suite Pro and DTM. So as long as you load up the DTM workspace and configure your network adapters to have, which it does for you automatically, the IP addresses, you can actually run through a lot of the stuff we went over today in the 61850 portion You don't even have to build up a workspace. We have it for you as samples.
Yep, great point, Matt. Okay, next question. I will just throw out to both of you. Is GOOSE limited to binary values?
No, absolutely not. So, typically you're not going to have like a current or voltage in there, but you can certainly transmit things other than just binary values. I mean, the most basic example would be our breaker position, which is just a double bit. So, 2 bits side by side that give you the possibility of 4 states, open, closed, intermediate for that fraction of a second, while the breaker or switch is neither open or closed. And then also there's basically a 4th error condition.
Okay. So more of a general question that we did receive, and again, Jackson or Matt, either one of you can take this. What is the exact role of SCL Navigator, and can this also be done in Test Suite Pro?
So yeah, go ahead.
Matt, yeah, go ahead.
So SCL Navigator works directly on the SCL files, your ICD, CIDs, IIDs, SCDs, whatever, right? You can add report control blocks, you can add data sets, modifications to communication sections. It's all about editing the file itself. Once you have the file itself, that's where you can supply that to DTM or Test Suite Pro in order to actually simulate or connect to or interact with the physical devices. So obviously all these tools do work with 61850, but they all have their own niches, and Navigator specifically is viewing, navigating, and editing the files rather than hosting and simulating them.
Okay. Another good question, this might be more for Jackson. Is GOOSE traffic limited to an individual substation?
So that's a great question. And it's got not a short answer. So GOOSE is a layer 2 communication protocol. So what that means is that the short version practically means it's not able to traverse a router without the use of a VPN or tunnel. So traditionally, I would say GOOSE was kept within a single substation, unless you were to use a VPN or tunnel in order to transmit the messages between them. But that was kind of the old way. Now there is the introduction of RGOOSE, or routable GOOSE. So we didn't cover it in our presentation. We will in a future one. Routable GOOSE you can think of as a variant that uses UDP multicast. So UDP is able to transverse a router. You can actually send it out on a wide area network. Because of that, and because it's now capable of leaving the substation, there's also security mechanisms that are encouraged or even mandated in some cases. So those security, can apply to layer 2 GOOSE. You can apply authentication and encryption using KDC, or a key distribution center. We have a lot of information about that on our website. We actually sell a protocol stack version that includes support for that. But yeah, that's the short version. Is if you're using routable GOOSE, then it's designed to leave the substation and be routable. If you're using layer 2 GOOSE, then you would need a tunnel or VPN. Otherwise, you need a flat network in order to have those messages go out on a wide area network.
Okay, thanks. Matt, this one might be for you, but feel free to send it over to Jackson if needed. What is the data miner in the DTM tool?
Maybe a typo there. The data miner is actually in Test Suite Pro. The data miner tool is not one that we showed off today, but it's very helpful when you're building the displays, like the custom display or the signal flow or whatever. It allows you to take the model of all the devices across your files that you provide at Test Suite Pro and kind of filter out and view the models of all the devices in a single place. So you might say, I only want to see X CBRs across all my devices, and then you can drag over the positions of all of your X CBRs or your different devices and actually have access to your switches and your breakers rather than having to go to the advanced client, choose one of your IEDs, scroll down to the position, drag that over and repeat that process. You can basically put it all into almost a flat view and apply a bunch of filters to get to the data you want a lot quicker.
Okay, thanks, Matt. I'll throw this question out to both of you. Are the tools for Triangle MicroWorks suitable for other relay manufacturers like NR, Siemens, ABB, Ariba, and Hitachi?
Absolutely, yeah. We are, vendor agnostic, let's say, and that's one of the beauties of 62850 because it is a standardized. Well, I was about to say protocol, but as we've just discussed, it's a lot more than just a communication protocol. But yes, absolutely, we work with every vendor's IEDs.
And I'd piggyback on that even a little bit. A lot of the vendors will actually purchase our own source code library and implement it in their devices. So you'll be using, our test tools to basically communicate with devices that might still be running our software.
Yep, good point. Okay, one more question. I don't understand when you would use client or server in 62850. Can you explain the difference?
So, yeah, I could take that question two ways, and so I'll try and answer both. So first, let's define what a client and a server is, in case that wasn't clear. So, in a broad sense, if I go back to, or if you can imagine the slide where I had kind of like a layout of a substation, and I talked about primary equipment and secondary equipment. Those pieces of secondary equipment are going to be servers typically, right? So they're going to either interface directly with pieces of primary equipment, our breakers and things like that, or CTs and VTs. Or in some cases, it might just interface with other pieces of secondary equipment, right? I might have a protective relay that is getting its sample value stream from one IED and interfacing with a second IED in order to trip the breaker. That's still going to be a server. So when I want to transmit any of the information from those devices up to my SCADA system, any of the devices up at the top at the SCADA level, they're going to be clients. And fundamentally what it means is that they're capable of subscribing to reports, that MMS or client server information that we spoke about. To answer the question the other way, why would I want to use client server communications as opposed to GOOSE or sample values? It's the SCADA communication protocol. So it is routable. It can transverse a router. It can go through a multi-tiered network. It uses TCP/IP. There's a lot of great things about it. If one piece of data changes in my data set, I'm only going to notify my higher level system that, hey, just this single piece changed, and my report therefore will be a little lighter weight on the wire. I hope that answers the question.
Okay. Another question actually just came in. With Triangle MicroWorks tools, may I use Wireshark to capture a specific traffic on the network?
Yes. There's no smoke and mirrors. I always like to point that out. Even though we are using a simulation tool, we could potentially pass data back and forth from one app to the other, but we don't do any of that. If you are running DTM like I did today and Test Suite Pro like I did today, MMS, if you open up Wireshark, you'll see that. If you are running GOOSE, you'll be able to see that. We've tried to provide tools such as the protocol analyzer, GOOSE viewer, report viewer, and stuff like that, that can actually go and make the signals that you might see in Wireshark a little more human readable. But if you really need to get down to the specifics of it, absolutely. All of the traffic is running off the same source code library that are in devices all around the world. So anything that you want to see, sample values, GOOSE, MMS, that's all out there on Wireshark.
Perfect. Okay, I think last question here. Can you have file transfer using MMS with Test Suite Pro?
Yes.
Absolutely. Yeah.
We have a whole tool for it, file transfer.
And I'll just add the note that that is also supported in DTM.
That's true.
Okay. Well, with that, I'd like to bring the webinar to an end. Again, thank everyone for joining and spending your morning or perhaps afternoon with us. please be on the lookout for additional information on the future training modules that we will be hosting. Okay, thanks everyone.